because section 4.2 is completely different. Not completely different, but it deals with two theorems that which can wait. So we're moving on to 4.3. 4.2 will not be skipped. We want to finish 4.3. So let's summarize, and I'll tell you what 4.3 is all about. Let's summarize what we know from the first derivative about the function. Am I still sharing? No, okay. What do we know? What does the first derivative tell us about the function? It gives increasing and decreasing intervals. So what do I know about this function between 0 and 30? Oh, it's increasing between 0 and 3.9, and it's decreasing between 3.9 and 30. Very clear. So it gives us the increasing and decreasing intervals. Then it gives us max-min. Of course, only if it changes sign. So this is a max because the function is increasing, the first derivative is positive, and this first derivative is negative. So that's why this is a max. And also gives us the min. Well, what else? And I should have started with this, critical numbers. So without the critical numbers, if a function has no critical numbers, cannot have max-min. If it has critical numbers, I have to investigate if it has max, if they turn into max-min for the sign change of the derivative. If the derivative doesn't have a sign change like this or reversed, there is no max-min. Good. So that was a summary of section 4.1. Now in 4.3, we're going to look at the second derivative. And no, we're not going beyond the second derivative, only the first and the second derivative. The second derivative will give us concavity. What does concavity mean? If the function opens upward or if the function opens downward. So it gives us intervals of concave upward, concave downward. What else gives us? A very important point called inflection point or points. What is an inflection point? An inflection point is when the function opens up till this point of inflection, and then it changes concavity. So here, my grandma taught me when I was very little, she said, well, you don't understand concavity? It's very simple. It does not hold water. It's concave downward. Here it holds water. It's concave upward. So from when a function changes concavity from opening downward to opening upward, this is called an IP, an inflection point. Of course, it can open upward and then continue downward. Same thing. This is still an IP, an inflection point. Of course, how do I find the inflection points? The same way I found the max-min, with critical numbers if you want, or when the second derivative is 0 or undefined, and then studying the sign. So what happens here when the function holds water, the second derivative is positive. So here, the second derivative is positive, like here and here. Here, the second derivative is negative. The function does not hold water. The function holds water, the second derivative is positive. Here it does not, so the second derivative is negative. So for the rest of the day today, we're going to look at the second derivative, determine concavity, if the function opens upward or downward, and inflection points. Okay. So I'm going to share my screen and go directly to 4.3. And we're going to come back to these two theorems. I will not forget. So what does the second derivative say about this? And we're going to discuss this, the first and the second derivative test. We already did. I did not wait till 4.3. We already did. Okay. So use the graph to find the open, so they're going back to the first derivative for a moment. So the open intervals on which f is increasing and decreasing, and then concavity and points of inflection. Okay, so let's choose a graph, any graph.
Two.
Okay, very good. So we want to choose 2. Look at that. Only simply because I highlighted it, it turned blue. Okay. Good. So we have it here. I always like to enlarge it on the screen so we can see it better. Okay. So notice that this function does not hold water till this point. Then it starts holding water till this point. When it stops holding water till this point. When it starts holding water again. So can anyone tell us how many points of inflection we see? So on number 2.
3.
Yes. So the first point of inflection is,
X equals 1.
so the point, 2, 2. The next point of inflection is 4, 3. And the last point of inflection is 5, 4.
Yeah.
Do we all agree with this? Agreed?
Yes.
So the function is concave downward between 0 and 1, 0 and 2, sorry. And also between 4 and 5. So concave downward and concave downward. So I'm going to write it f concave downward on 0 to 2 union 4 to 5. And it holds water on 2 to 4 union 5 to 7. So let's see. Inflection point 2, 2, 4, 3, 5, 4. Concave downward on 0, 2 union 4, 5. And concave upward on 2, 4, 5, 7. We're also asked to identify the increasing and decreasing. Okay, increasing, increasing. So increasing between 0 and 1, not the y values, the interval. So increases between 0 and 1, and 3 and 7. So f increasing 0, 1 through 3 and 7. And f decreasing, obviously between 1 and 3. Let's check again. So it's decreasing between 1 and 3. Right here. 1 and 3. Any questions on the graph? And how to identify concavity, increasing and decreasing, and inflection points. Obviously, this function has an absolute maximum, has an absolute minimum, none of which is a relative, of course. Absolute minimum is 0. Absolute maximum is 2, 4, is 6. It has a relative minimum at 3, 3, 1, and it has a relative maximum 1, 3. This is the absolute minimum, and this is the absolute maximum. This is an inflection point, and this is an inflection point, and this is an inflection point. Moving on. So, find the intervals on which f is increasing or decreasing. We already know that. And find the local max and minimum. We already done that. I want to move on. Find the intervals on which f is concave upward. I didn't wait till here. So that's why we chose functions from 4.1, and we already did all this. Find the intervals on which f is concave upward or concave downward, and find the inflection points. Okay, so let's choose. Since we haven't looked at a natural log, other than just a simple natural log, let's choose something like this with a natural log this time. Which one?
No preference.
Which one?
No preference.
Yeah, it doesn't matter.
Okay, so let's look at 21 then. So f of x equals natural log of x squared plus 5. Well, let's see what this one gives us. So forget about max min and increasing and decreasing. I want to focus on the second derivative. So therefore, I find the first derivative as being 1 over x squared plus 5 times the inner function prime. So this is 2x over x squared plus 5. Directly moving on to the second derivative. Now this is a constant. I prefer, because I don't have anything else at the top. 2x is the same with 2 times x over. And I will do that for simplicity. So I don't have to worry about that 2. It doesn't mean anything anyway when it comes to the second derivative. Top function prime is 1 times the denominator minus the top times the denominator prime, which is 2x, over x squared plus 5. X squared minus 2x squared. So it's negative x squared plus 5 over x squared plus 5 squared. And you know me, I am allergic to a negative leading coefficient. We finally obtained the second derivative. Yay! Well, I have two options. Either is 0 or undefined. Similar idea, similar situation with the first derivative. So this is positive always. It can never be 0. And x squared plus 1, the domain is all real numbers, but this is always positive. It will never be 0. So I won't even bother with that. So it will not be anything coming out from undefined. But what about 0? Negative 2 is a factor outside, who cares? So when is this fraction 0? And I know Amanda already told us like 3 times tonight, when x squared minus 5 is 0, or x equals plus or minus 5. Square root of 5, of course. So x equals plus or minus the square root of 5, which is approximately 2.4 something. Square root of 5, 2.24. So approximately 2.24. I said 4 and I wrote 5. Okay, so of course, the analysis is done with a similar table as before. And we have f prime of x, and we have f of x, and we have the second derivative. I'm not going to fill the first derivative out with anything because we skip that. The domain is all real numbers. So we only want negative 2.24 and 2.24. 0 and 0. I have to study the sign of the second derivative. I will not study the sign of the denominator. I refuse. It's a waste of time. And I would like to plug in a number to the left of negative 3, in the middle, and to the right of 3. So a number here, which is 0, which will be the easiest, negative 2 times negative 5. And when I plug in negative 10, this will be positive with minus in front. When I plug in 10, this will be positive with minus in front. So therefore I know intervals of concave downward, negative infinity to negative 2.24, union 2.24 to infinity. Interval of concave upward between negative 2.24 and 2.24. In order to determine the inflection points, I have to plug this in. Now, are these inflection points? Of course, because the second derivative is 0 and it changes sign. So this comma this number will be an inflection point. We say IP. This comma this number, not 0, 0 is for the second derivative. This comma this number that I did not determine yet will be an IP. Why? Because the second derivative is 0 and it changes sign. So this is how we determine concavity, intervals of concavity, and inflection points. So I'm going to put this in the graphing calculator and plug these numbers in. I will get the same answer because positive or negative, this will be the same number. And since it's the same number, I'm just going to do it real quick. So I have natural log of, what was it, 2.24 squared.
Negative.
It doesn't matter. If I
Yeah,
square it,
yeah.
it will make no difference. And so I get 2.3. So 2.3 for both of them. So the inflection point is negative 2.25 comma 2.3, as well as 2.24 comma 2.3, and negative and positive 2.3. So this is the analysis for concavity. Now we can go back and analyze the first derivative if we want to, because I want to connect the dots. So let's do that. But I wanted to show as soon as possible how to determine concavity and inflection points.